Hi everyone and welcome back to Analog Electronics Lectures. In today's lecture we will talk about the operational amplifier. We'll go in depth into the operational amplifier. We'll study the rules of the operational amplifier, the different configurations of the operational amplifier circuits. We'll talk about the inverting amplifier, non-inverting amplifier, and also we'll study in depth what is the circuit configurations that are necessary to apply in operational amplifiers or op-amps. As we said, the operational amplifier is an amplifier that can make amplification plus some operations, simply like this. We have two inputs. This operational amplifier takes the difference between these two inputs and make amplification for this signal here on the output. So let's say if we have a small signal here like this signal will be larger on the output, okay? And also this kind of amplifier, the operational amplifier, also make operations, addition, subtraction, division, multiplication, integration, differentiation, and so on, okay? For this amplifier, there are some rules that are applied on this amplifier. If we consider this an ideal amplifier, not practical, the ideal amplifier. So we said that AV, the gain of this amplifier is equal to how much? This is infinity. And the input resistance is how much? Infinity. And also the output resistance will be how much? 0. So these are for the ideal operational amplifier. And now we have also two rules. Rule number 1, the voltage rule. What the voltage rule says? The voltage rule says the output attempts to make the voltage difference between the inputs 0. So V plus minus V minus is equal to 0. So this is rule number 1. So as if we said that we have output here, this output signal modifies itself in order to make the difference between these two inputs to be 0. Okay, so this is rule number 1. Rule number 2, the current rule. The current rule says the inputs draw no current. Since we have infinity input resistance, so there is no current flowing in the operational amplifier. So the current here, I, is equal to 0. And the difference here is equal to 0, right? Now let's try to use these rules, the voltage rule and the current rule, in order to apply or to find the gain of the non-inverting operational amplifier. So here we have the non-inverting operational amplifier. The non-inverting operational amplifier, by definition, the circuit is like this. We have the op-amp circuit, V plus, and exactly similar to the circuit that we studied last time. Here we have two resistors and in the middle here, it's connected to the inverting input. So this is V plus, this is V minus, and this is V out from here to here, V out. Okay, and let's say this is R1 and this is R2. Where's the input? The input from here to here, plus minus V input. So from here to here, this is V input, and from here to here, this is V output. So this here, of course. Okay, now let's try to apply the rules of the operation amplifier on this circuit. Now we said that the voltage rule, V plus minus V minus is equal to how much? Is equal to 0. And this is the voltage rule. Okay, from this we can say that V plus is equal to V minus. And from this circuit we know that V input is equal to how much? To V plus this value, right? Now look at V minus here. V minus is connected here. So we can use the potential divider, the voltage divider, right? So V minus is equal to how much? V minus is equal to V out times R2 over R1 plus R2. Okay, so the voltage here, V minus, is equal to this resistor over this plus this times V out. Okay, times V out. And because V plus from here is equal to V minus, and V plus also equals to Vn, so we can replace this V minus with Vn, right? So we can say that Vn equals to V out times R2 over R1 plus R2, right? Now we have equation with V out and Vn. We can easily find the relation between the output and the input. And this, the relation between the output and the input is what? Is the gain. Because you said the gain is V out over Vn. So we can easily say that V out over Vn equals to R1 plus R2 over R2. And this is the gain of this non-inverting operational amplifier. Okay, now let's say we want to find, we want to design an amplifier with, for example, 10 gain to amplify 10 times the input. Okay, what to do? We select these resistors in a way that their value must be 10 and so on. Okay, and let's say this non-inverting amplifier has an input of sine wave like this. So the output must be how much? Let's say this output is, let's say the gain is 2, for example. If the gain is 2, so this value will be non-inverting. It will be same polarity, but double the value. If this is 1, this will be 2. The peak will be 2. Okay? Let's explain another important topology for the amplifier, which is the inverting amplifier. The inverting amplifier can be drawn like this. We have the same circuit, okay? But for this one, the non-inverting input will be grounded, okay? And the feedback will be given to the inverting input. So this non-inverting input will be grounded. Here we have V out, okay? And the inverting input will be connected to a resistor, and we have a feedback resistor here to the output, okay? So the input from here to here, this is V input. Remember, this is not connected directly to the inverting input. Let's say this is R1 and this is R2, okay? And this is V minus and this is V plus, okay? Now, using the voltage rule again, we know that V plus minus V minus equals to 0, right? So V plus is equal to V minus, and this is the voltage rule. Now, from the diagram, V plus is grounded, so V plus is equal to 0, right? Because it's connected to the ground here. And because V plus equals to V minus, so both should be equal to how much? To 0, right? So this is grounded, and this is taken from the voltage rule. So V plus is equal to V minus is equal to 0. Now, as if this V minus is grounded as well, right? So this, we said that V plus equals to V minus, and V plus is grounded. So V minus can be also considered as grounded. And the voltage from here to here on this resistor will be how much? The potential from V out here to the ground. So the voltage will be V out. So voltage across R1 is V out. Okay? And voltage across R2 is V in. Why? Because again, from here to here, this is grounded, so the voltage is V input, right? If you remember, we said that the voltage from here to here is, let's say, and this is V in, so the voltage on the resistor is V in, okay? Again, if we have a resistor like this, and this is V1, and this is V2, so the voltage across this resistor is how much? V1 minus V2. If the value of V2 is 0, so V1 minus 0 is V1, and so on. So here we have the same thing. V minus is 0. The voltage across resistor number 1, V out, this value, minus V minus. V minus 0, so the voltage across the R1 is V1, V out. Again, here's the same thing for resistor number 2. The voltage across this resistor is V input minus V minus. Okay? Now, when V minus is 0, so V input minus 0 is V input, so the voltage across V2 is V input. Okay? Now, since we have infinity input impedance or input resistance inside the operational amplifier, so here is infinity, we said that according to current rule, the current that's coming inside this amplifier is equal to how much? Is equal to 0, right? It's V input, V output, R1, R2. Okay? So we said, okay, according to the current rule, the current inside this amplifier is 0. Okay? And if we assume that we have current here, I 2 inside the resistor R2 and current here inside the resistor R1 I1. So because the current here is 0, so I1 must be equal to minus I2, right? Because they are assumed in the opposite directions. Okay? And this is the current rule. Now, let's try to gather our information. We have I1 equals to how much? V out minus V minus over R1. And this will be equal to V out minus V minus how much? 0 and R1. So this will be V out over R. The current through resistor R1. And the current I2 equals to how much? V input minus 0 over V input minus V minus over R2. So this will be V input minus 0 over R2. Okay, this is R1, this is R2. And here V input over R2. Okay, since here we have I1 equals to minus I2, so this will be equal to minus this, right? So V out over R1 equals to minus V in over R2. And from this we can say that V out over V in is equal to minus R1 over R2. Okay? And this is the gain for this inverting amplifier. Why we said inverting? Because the output is negative. The gain is negative. For example, if we say that this amplifier has a gain of 2, so if the input signal is like this, the output signal will be how much? Like this. So this is 1. This will be how much? Minus 2. And this, for example, if this is minus 1, this is plus 2, the peak. And so on. So this is inverting. So just for accuracy, this is minus 2. Okay? Because you said G is minus R1 over R2. R1 is the feedback resistor and R2 is the input resistor. Let's come back to the non-inverting amplifier. We said we have amplifier that like this, plus minus, and the input is taken, given to here. We have output, and here we have two resistors. One is connected to the inverting input, and the other one is connected from the inverting input to the ground. Okay, and the output here is V out, and the output here is V in. The input here is V in. Okay, and this is V plus, V minus. Okay, now, and this is R1 and this is R2. Now let's try to make some modification for this circuit. Let's say if this R1 is 0, for example. So 0 means short circuit. Okay, and R2 is infinity. Infinity means open circuit. So here, as if we disconnect this resistor and throw it on the dustbin. Okay, so this will be open circuit, and here this will be connected directly to the input. What's happening at this moment? So we know that for the non-inverting amplifier, V out over V in equals to R1 plus R2 over R2. Okay, so this is R1 over R2 plus R2 over R2 is 1, right? When R2 is infinity and R1 is 0 or any value, okay? Let's say it's 0, okay? Because we replace it by 0. So what's happening to V out over Vn? V out over Vn equals to 1. Okay, so here we have a unity gain for this circuit. And we call this circuit is what? The unity gain buffer amplifier. Okay, or we can call it what? Voltage follower. At first sight, this might not seem like a very useful circuit. However, it has a high input resistance because we said the amplifier has infinity input resistance and a low output resistance. So here we have very like zero output resistance, and therefore this circuit can be useful as a buffer amplifier. Next time we'll continue talking about different configurations of operation amplifier circuits. We'll see the differential amplifier or the subtractor. We'll see the voltage to current converter. And also we'll see the inverting summing amplifier. We'll look at many circuits like the integrator, differentiators, and many other circuits. So see you next time.